So this is a very important concept in linear algebra and has its applications in computer science, engineering, and math, of course. Now, section 5.1 is named the same as the chapter name, but because we are now introducing what are eigenvalues and what are eigenvectors. The basic question that we are looking at is that when we have an n by n matrix, a square matrix, we want to find out whether there are non-zero vectors in Rn such that when you multiply the vector x with the matrix A, does it give a same vector back multiplied by a constant? In other words, we have vectors x such that Ax is equal to lambda x, where lambda is a value, a number, and it can be real and it can be complex as well. We are only going to look at the one with real values of lambda. So this lambda is called the eigenvalue of the matrix A. So we multiply the matrix by the vector by the matrix, and we end up getting a scalar time the vector, the same vector. So the vector x in this case is called the eigenvector of A, corresponding to lambda. Because there could be more than one lambdas for a matrix as eigenvalues. Here is an example that A be this matrix and U and V are given. So we want to check are U and V eigenvectors of A. So either U or V or both. We have to check. So here is something I have done already here. So what we do, we have A and we have U. So we will find out what is AU. When I did AU, I got answer as 0, 0, 0. Now 0, 0, 0 is just 0 vector. It is not U vector. So we cannot say that this is equal to 0 into U, because U is, here the vector is 0, not the lambda. So this is not U is not an eigenvector. What about V? So when we multiply V, I am getting 1, I multiplied the vector 1, 0, 0 with the matrix. This is V and this is A. So, and I'm getting back 1, 0, 0, which means I'm getting AV is equal to 1 times V. So in this case, the lambda is 1. So V, the vector V is an eigenvector of A corresponding to the eigenvalue 1. Okay. Note, if X is an eigenvector of an n by n matrix corresponding to the eigenvalue lambda, then every non-zero scalar multiple of X is also an eigenvector of A. So here is kind of a proof. So we say, okay, let U be equal to C times X. So U be a vector which is a scalar times vector X, and we are assuming that X is an eigenvector. So if X is an eigenvector, it means AX is equal to lambda X. So AU will become A times CX. So A times, when I say A times lambda X, actually I should say A times CX in this case because we have a C here. So we start by multiplying the vector, given vector, with the AU will be A times CX. Now we know by properties of matrices. So if you have a matrix multiplied by a constant or a scalar, we can move the scalar onto the left or right. So we move the c to the left, we get c times a times x. Now we can call this c times, well, ax is equal to lambda x. Remember, so ax here becomes lambda x, so c times lambda of x, which can also be written as lambda times c of x, which means lambda times u. So this means au is equal to lambda u. So now we will see this by geometrically. So let V1 and V2, so it's better to have a 2 by 2 matrix. It's easier for simple to see. So V1 is vector 2, 1, and V2 is 0, negative 1, and A is this given matrix. We see that AV1 gives us 4, 2, and I can pull out the 2, and I get 2 times 2, 1. What is 2, 1? That is our V1. So this can be written as equal to 2 V1. So V1 is the eigenvector of A corresponding to 2, and then we check V2, and V2 is 0, negative 1, but when I multiply it with A, I get 2, 0. So which is not a, so V2 is not an eigenvector. Let's see geometrically what is happening here. So you notice that when A is being multiplied with A gets multiplied with V1, we got 2 times V1. So where is 2 times V1? It will be 1, 2, and then at 2. So what happened? So this is 2V1 from the origin till the here. This total is 2V1. So what did the multiplication or the product with the matrix did? It stayed in the same direction, or the stayed along the same line where V1 is. So you can see every multiple of V1 will be along this line. If you recall, this is something like a subspace of Rn. In this case, subspace of R2, this line, it contains all the vectors which are multiples of V1. So it doesn't change the direction. Multiplication of A with A didn't change the direction of the or position of the, I would say position of the vector. So usually when you multiply a vector with a matrix, it will change its position. For example, AV2. So V2 is down here. But when we multiply with the matrix A, what does it become? It becomes 2, 0. So where is 2, 0? 2, 0 will be here. So this is AV2. It has been changed, but the eigenvector, in other words, now when we have eigenvectors and you multiply them with a given matrix whose eigenvectors those are, they will not change the direction. Okay, moving back. Okay, now, so we saw just a few minutes ago that A times X, if you have a matrix, an eigenvector X, an eigenvector of matrix A, then any multiple of eigenvector will scalar multiple of the eigenvector will also be an eigenvector for A. I just showed you that with the graph in geometrical case and then with the proof over here. The second point to note here is that it is also true that if x1 and x2 are two eigenvectors corresponding to the same, this is important, same eigenvalue lambda. So previously we noted or we saw in the two examples that were given, example 1 and down there I showed you with the 2 by 2 matrix, we had two vectors which we were checking, and each of them were, one of them was not an eigenvector, and the one which was an eigenvector was associated to this lambda, to the eigenvalue, and so we had one eigenvalue and one vector, but it's not always true. With one eigenvalue, there could be more than one vectors associated to so for one eigenvalue, there can be more than one eigenvectors. So if we have two eigenvectors which correspond to the same eigenvalue, then the sum of these vectors is also an eigenvector. So basically what we are saying here is, let me show you what geometrically it means. So geometrically you can imagine that if we have two eigenvectors for one eigenvalue, then it means we are in a plane. So let's say these are the two eigenvectors, u1 and u2. So they form a plane. So right now I am in the plane of this paper. So if we add them, remember the triangle law rule. So this will be the sum of u and v, sorry, u1 and u2. So this will also be in the same plane. So this will also be an eigenvector. And we can show algebraically. Okay, I think we don't have space there, so I will show you here. If our statement is that if u1, u2 are eigenvectors of A corresponding to lambda, so 1 lambda, then u1 plus u2 is also an eigenvector. And corresponding to lambda. Okay. So what we know is that u1 and u2 are eigenvectors. So it means a u1 is equal to lambda u1 and a u2 equal to lambda u2. What about u1 plus u2? A u1 plus u2 will be now by properties of matrices. We can write a u1 plus a u2. But a u1 is lambda u1 and the other is lambda u2. So which means equal to lambda u1 plus u2. So note here in this last one, we get a times u1 plus u2 is equal to lambda times u1 plus u2. Now this is kind of a neat proof, and you can expect this in the exam. u1 plus u2 is an eigenvector. So this shows that u1 plus u2 is an eigenvector of A corresponding to lambda. So this is a neat proof. Actually, what does this prove? First, we saw that A times Cx gives us lambda times Cx. And now we saw A times x1 plus x2 or u1 plus u2 gives us lambda times x1 plus x2.